Hello everyone, my name is Anna Carnes and my presentation is about very high temperature reactors. Very high temperature reactors are thermonuclear reactors that generate very high temperatures, typically 900 degrees Celsius or greater. Most commonly, they would use uranium fuel, a graphite moderator, and a helium gas coolant. Other very high temperature reactors use different materials, which we will cover later on. Most very high temperature reactors are conceptual or in the process of being tested. There are, however, several reactors that share different aspects of very high temperature reactors that have inspired a new wave of Generation 4 reactors. One new kind of fuel, called triso particle fuel, seems to be the best potential energy source. Very high temperature reactors can have one of two types of coolant. There are liquid salt very high temperature reactors and gas-cooled very high temperature reactors. The liquid salt reactors came up less frequently during my research. The liquid salt is typically a fluoride salt, which have melting points between 320 degrees and 500 degrees Celsius. They are less versatile because they require more space for a water source to generate steam, and they do not reach the same temperatures that most Generation 4 reactors want. Gas-cooled reactors, on the other hand, can reach higher temperatures, 900 degrees Celsius or greater. They can also be built in smaller units. This is because they do not need a water source to generate steam. The gas coolant, when heated, can be used directly to turn the turbines of the gas generator without the use of a heat exchanger or water. With a heat exchanger and water, the space needed would increase and the efficiency would decrease. Reactors that use helium to turn a gas turbine are called gas turbine modular helium reactors. Many of the sources I used very high temperature reactors and high temperature gas reactors interchangeably. Most future very high temperature reactors will probably be gas cooled with helium as the most common coolant. Because these plants can be built in smaller units, they can be placed in less convenient places and supply energy to many previously unreachable areas. Triso fuel particles are the future fuel source with the most potential. Triso stands for tristructural isotopic. Right now, this fuel is being rigorously tested and so far has been very successful. It even broke the world record for the highest maximum burnup of 19% over a 3-year testing period. Triso fuel particles are made up of a fuel kernel, typically uranium dioxide, and 3 layers of alternating graphite and ceramic material. These coatings prevent fission products from escaping the particle. They can be arranged into cylindrical pellets or billiard ball-sized spheres. The ceramic coating is typically made of silicon carbide, which can withstand extremely high temperatures. These particles are incapable of melting in very high temperature reactors. Because of this and their retention capabilities, they will drastically reduce the potential for meltdowns. They are also extremely hard to repurpose because of the ceramic coating. They're very resilient. Triso particles can be arranged in 2 ways. In prismatic block reactors, the triso particles are arranged into cylindrical pellets that go into interlocking hexagonal prisms. This design is more common in the US. They can also be arranged into pebbles, which is more common in other countries, such as Germany and Japan. In a pebble bed reactor, the triso particles are arranged into spheres with a 6 cm diameter. Then they are placed into graphite sheets and into the core. The pebbles contain approximately 15,000 triso particles each. They weigh about 210 grams, 9 of which are uranium. Also, in the diagram on your right, it says that the shield is concrete. But in very high temperature reactors, the shield would typically be made from a ceramic-based material, similar to that of the triso particles, to protect the rest of the reactor from the high temperatures inside of the reactor core and any radiation in the event of an emergency. Some of the relevant topics we've covered in class were moderator properties, cross-sections, and the nuclear fuel cycle. Graphite is a great moderator because it has an extremely low absorption cross-section. Its cross-section is approximately 100 times smaller than that of water, which is a common coolant used in other lower temperature reactors. Helium also has a low absorption cross-section and will remain non-radioactive even when exposed to radiation. We also talked about the nuclear fuel cycle, which mentions enrichment and the repurposing of spent fuel. TRISO fuel is incredibly difficult to repurpose because of its ceramic coating. Because of this, it is typically stored in a separate location and replaced with new TRISO particles. However, it reduces the risk of meltdowns in the reactors because of its ceramic shell. The uranium in these particles is low enriched uranium and is enriched to nearly 20%. One of the potential uses for this technology is to use the energy from very high temperature reactors to power hydrogen production plants. One of the next steps in improving our energy sources is to reduce carbon emissions. If very high temperature reactors use uranium dioxide instead of carbon-uranium compounds to power these facilities, we could drastically reduce carbon emissions, especially if these reactors become more widespread. They are much safer than any previous reactors and take up less space. They should be stable enough for people to live in close proximity to the plants in the near future. This would allow more people to utilize and have access to nuclear power. It would also allow us to replace fossil fuel power plants with nuclear and hydrogen energy sources. Currently, most very high temperature reactors that are in use are strictly experimental. There are, however, a few other reactors that inspired the designs for the new generation of very high temperature reactors. The VHTR in Japan was created by the Japan Atomic Energy Research Institute. It was called the High Temperature Engineering Test Reactor, or HTTR for short. It is a helium gas-cooled reactor with a graphite moderator and has been used to test potential safety hazards and the safeguards in place to prevent and protect against these accidents. It has a maximum outlet temperature of 950 degrees Celsius. And in 2015, a hydrogen production facility was paired with the HTTR to use nuclear energy to power hydrogen production. So far, the results have been very promising. The HTR PM in China is a small modular high-temperature gas-cooled reactor. Originally, the modular high-temperature gas-cooled reactor, it was renamed to High-Temperature Reactor Pebble Bed Module. Construction began in 2013, and the design was based off of the previous HTR-10. Both use helium gas as a coolant, and it is expected to be the first Generation 4 high-temperature reactor put into use. The AVR reactor in Germany was built in the 1960s. It was the first pebble bed reactor, and it was highly experimental. It was also one of the first reactors to use helium gas as a coolant. There were many issues like fission products leaking during depressurization and fuel temperature instabilities. It was given the nickname shipwreck due to all of its accidents. It shut down in 1988 and was officially decommissioned in 2003 by the government. The technology tested here inspired the HTR PM in China and many other reactors. The gas turbine modular helium reactor was built in Russia based on the General Atomics design. It would burn weapons-grade plutonium to create electricity with 50% efficiency from the heat. This was very high for the time. It was originally built to dispose of Soviet nuclear warheads, and it could generate 100,000 tons of hydrogen per year. It's a small modular reactor, which is cheaper and easier to construct. This is the inspiration for many of the Generation 4 prismatic block models. Thank you for your time. I hope you enjoyed hearing about the intricacies of very high temperature reactors. The next two slides include all of my works cited and references.